Okay, YouTube, in this video we're going to confront how we kind of compare graphs of functions versus graphs of sequences. And so in our last video we looked at what a sequence is. It's just a list of things that occur in order such that you have a first, second, third, fourth thing. But essentially what they are the same as functions, but where our domain is just the set of counting numbers. So we only plug in things starting at 1 and going on forever and ever. So what I want to do is this. Consider the graphs of f of x equals 1 over x. Now 1 over x, by the way, this was our rational function that had an asymptote here and an asymptote here, and it had two branches. But if we just look at just the right side right here, that's what you're seeing in this graph right here. But this is the graph of, let's just get that out of there. This is the graph of f of x equals 1 over x. And we can see that as we plug in any x value, we'll take 1 divided by that value, we get some y value back. And so the domain of this being all real numbers, every x value gets plugged in and every y value gets spit out because of that x value. Whereas when we look at the graph of a sequence here, now first things first, I want you to notice this. We're representing this rule, not in function notation, f of x notation, but in a of n notation or in sequence notation. So I want you to know that you will sometimes maybe see it represented this way. A of n is 1 over n, which is totally kosher. We say that this thing is also awesome. So we say that a subscript n or a sub n is just 1 over n. You don't have to write the cusp, but that's how I found it in this screenshot from our textbooks. So let's go ahead and take a look at what you see here. They are the same thing. You see the same values reflected here, except for, I don't mean to say a mathematical reflection, but you see the same values on each graph, except for in the function notation, all x values are represented. In the sequence notation, only the natural numbers are represented here. So one thing I want to do is I want to make sure that we represent this appropriately here. We say that these are the terms or the term number, and I want to make sure we label the x-axis here. So our term number is represented by n, and you see up at the top here a sub n. We're going to say that this is the term value, whatever it is representing, and we're going to say comma, and I'm going to rewrite this here a sub n. And so that's what we're looking at here, and I would say that we never connect the dots. And so what this means is our domain has gaps in it, or it's got holes in it. We refer to this as having a discrete domain. So it has a discrete domain, and when we refer to a discrete domain, that is essentially the opposite kind of idea of what we refer to as something that has a continuous domain. So the difference between a continuous domain and a discrete domain is that the continuous domain, say for instance here, includes all x values between 0 to infinity, whereas a discrete domain has gaps or holes in it. And so this starts at 1 and goes on forever and ever. So if we were to take a look at our very own graph, let's go ahead and do this. We're just going to sketch a graph. The first say 5, oh my goodness, it looks horrible. The first 5 terms of the sequence. You might be asked to do this. 5 terms of this sequence, and maybe this sequence represents something. For right now, what we'll say is this: how about the amount of money in your savings account over time? So I know that maybe like you start with $100 in there and it's going up by $30 a week or something like that, where n is the number of weeks, and then a sub n would represent the amount that you have in there. So I know that at time 0 here we'd have like $100. Essentially, if I wanted to graph the first 5 terms of this, I would say that this is something that looks very linear to me. And so for linear things, recall that our slope or our rate of change is the coefficient of our variable here. So I would say that n, its coefficient is 30. So I would say that it's got a slope value that would be like 30 for a function, and then our b value, this constant here, b would be like 100. So to graph this, what it would look like would essentially be this, and I'll just kind of move this. Let's move this down. See if I can do that. Oh, that's better. Let's make that bigger also. This is much better. Let's put on the first 5 terms. So first 5 terms, our term value goes down here. 3. Oh, it could be done better. 3, 4, 5. We'll label 5. I'm going to label this n, or the term value. Okay. And so if I were to look at this in terms of a context here, if this was like my savings over time, let me try this again here. We could say that this is like week number, even though it's the term number. And then we could say savings account amount, if that were the case. But I noticed that I would have to start at 100 here, and it's going up by 30 every week. So maybe if I go by 50s here, we'd say that would be 100 right there. We'd say this is like, maybe 200 right here. I'll label it 200. And maybe we can get away with this here. Maybe 250, 300 would be up here. I could do a better job. But we'd say that at week 0, if we say, what is A0? You plug in the 0 here. We get 3 times 0 here. We get 100. So our first data point is going to be at this 0, 0, comma 100. And then as we go to the right here, we plug in a 1. You could see that what's going to happen here is we're going to get 100 plus 30 times 1, which is 100 plus 30 and 130. So we say at our first week, I'll go ahead and label these here. Our first week is 130. If we're going by 50s, that would be right around this neighborhood here. Our second week would be 160, would just be north of 150. We'd have 190 on our third week here in our account, 190 to 220 in this next week here, and then 220 to 250. That would be like, maybe right in here. And so we would just leave it this way. We wouldn't connect the dots on this, but that's how we would confront the graph of a sequence. Cheers.